Okay, welcome to the session on metaprogramming. Our first speaker today is here. Her name is Ningning from the University of Cambridge, and she's going to tell us about staging with class.
Test. Okay, cool. Thank you everyone for coming to this session. And I'm Ningning, and this is joint work with my amazing collaborators, Matthew, Andrews, Nick, Jeremy, and Meng. So we will start with a bit background on multistage programming. Multistage programming is a well-established technique to generate efficient code with predictable performance. Essentially, while normal programs take some input and produce some output, multi-stage programming divides the compilation into multiple stages. And in each stage, the program is given some input and is partially evaluated to that input to generate efficient code for future stages. The key idea of multi-stage programming is it provides a type code that represents information available in a future stage. There are two standard staging annotations. A quotation is a representation of the expression as program fragment in a future stage. So if E is of type int, then the quotation of E is of type code int. And a splice extracts the expression from its representation. So if E is of type code int, then the splice of E is of type int. Let's take an example. The hello world example of multi-stage programming is the power function, where we would like to calculate n to the power of k. In the definition of power pattern matches on k. So if k is 0, it returns 1, or otherwise it recursively calls itself with k minus 1. And we can also define a function power 5 that fixes the exponent to 5. In this case, because this 5 is provided statically, we can consider this 5 is provided at an earlier stage than n, and we can use multi-stage programming to generate efficient code for power 5. To do so, we will define a staged definition of power, where the type of k is int, but the type of n and the type of the result of the program are of type code int. And when k is 0, we will use the quotation to turn int into a code int. Or otherwise, we will use the quotation to build a larger expression, and within the notation, we will use a splice to turn code int into int. And now, the definition of power 5 simply calls power with the static 5 and the quotation of n, and it uses a top-level splice to enforce code generation. In this example, we will be able to generate the definition of power 5 like this, where all the function calls and multiplications have been unrolled and inlined. That is, we successfully eliminate the abstract overhead of power. This is very exciting because we are writing power as a high-level function, but the definition of power 5 is defined in a very efficient manner, and we can use the same mechanism to generate power 4, power 6, or using the same mechanism. But how does it actually generate this efficient implementation of power 5? Well, let's dive into the evaluation process step by step. First, this power 5 has a top-level splice, so it enforces the evaluation of the expression inside the splice. And we essentially unfold the definition of Q power with the argument 5 and the quotation of n. Now, this expression has a top-level splice and a quotation, so we can consider them cancel each other out, which leaves us this. And the quotation and the splice cancel each other again for n, and we get this. At this point, the top-level splice on Q power enforces the evaluation of 5 minus 1, which reduces to 4. And at this point, if you compare with this expression with the expression we started, you can notice we have the same expression, except this 5 is replaced by 4. So if you keep evaluating this expression, we will get n times n times n times n times n until this exponent becomes 0, in which case we will get 1. Okay? So now this technique sounds very exciting, and it looks like the multistage just works well. However, there is one thing that we are not very satisfied with this example. That is, in the type of this example, we restricted the second argument to be an integer. But the power works for any real numbers, not just integers. So we would like to generalize the type of this function to be able to apply to any real numbers. And I'm a very proud Haskell programmer, so I know that I will be able to do it using type classes. Here, I generalized the type of this function to take a type class constraint number a. So now this function can be applied to any instance of number. And we would expect this program continues to work. It is somewhat surprising then that this function actually fails to compile in the latest implementation of typed template Haskell in the state-of-the-art Haskell compiler GHC. And the error message here is also mysterious. The compiler complains that it cannot find an instance here. This problem is interesting as it is not restricted to Haskell. Type features similar to type classes, for example, implicit in Scala, can suffer from a similar interaction between multistage programming. And OCaml is also developing supports for implicit and multistage programming, so we will expect a similar problem to happen for OCaml. In this talk, I'm going to argue that the current implementation of typed template Haskell is unsound in the sense that splicing a well-typed code block can raise a type error. And inspired by this unsoundness issue, we are going to propose a source calculus which models type classes, multistage programming, and a novel construct staged type class constraint that resolve the subtle interaction between the two. The source expression then elaborates to the core calculus with quotations and a key innovation splice environments that gives more implementation freedom about quotations. And our work provides a solid theoretical foundation for integrating type classes into multi-stage programs, and it is easy to implement and stays close to existing implementations. Now let's move to the first part of the talk where we introduce our source calculus. So to be able to fix this unsoundness issue, we first need to understand what the problem is. And we start by asking this question: how does multi-stage programming ensure type safety? If we write a program like power_n that we would like to evaluate at an earlier stage, as indicated by this top-level splice, but relies on information that is only available in a later stage, in this case n as the first argument of q power. The evaluation of this expression will get stark, as we don't know how to evaluate n-1 without knowing what n is. So we need a notion of well-stagedness that can correctly reject this program. In multi-stage programming, well-stagedness is expressed using the notion of a level. First, let's be a little bit formal, and we rewrite these two derivations using a typing constraint, a typing judgment. Here, the judgment basically says that under the type context, which stores types for variables, the expression has some type. And we can define the typing rules for quotation and splice correspondingly. With well-stagedness, we further attach to the judgment a natural number n that indicates the evaluation order of the expressions. For quotations and splices, quotations increase the level of the expression as it essentially says the value of the expression is only needed in a future stage. And the splice decreases the level of the expression and it enforces the evaluation of this expression in an earlier stage. And importantly, because the typing is also labeled, the typing context will also be labeled, in the sense that when we type check a function, the local variable introduced by the function is also bound at a particular level. And well-stagedness is enforced by the level restriction, where each variable is used only at the level in which it is bound. So we can correctly reject this q power n, as this local variable n is introduced at level 0, but it is used inside a splice at level -1. With level restriction, now we can go back to our problematic example and check whether this program is well staged or not. It appears so because all local variables k and n are introduced at level 0, and if you check it, they are only both used at level 0. So we should be able to conclude that both programs are well staged. Oh, are they? Maybe this program is like an iceberg, and we are only looking at the tip of it. And the problem comes from the unobserved part of this program, which in this case is type classes. In particular, type classes don't have direct operational semantics. Rather, they are implemented by dictionary parsing elaboration into a simpler language without type classes. After elaboration, the number A type class constraint corresponds to an extra parameter for the corresponding dictionary, and this dictionary is explicitly passed around to satisfy other type constraints. Now we can observe the problem. In the definition of Q power, this dictionary is introduced at level 0, but it is used inside a quotation at level 1. And similarly, in the definition of power 5, the dictionary is introduced at level 0, but it is used inside a splice at level -1. So both programs are ill-staged. Now the question is, how can we fix this problem, and how can we write a well-staged definition for Q power? We resolve the static interaction between type classes and multistage programming in our source calculus. And the key idea is that while we use code int to indicate that an integer has been staged, we use a normal construct stage the type class constraint, this code C, to indicate that the type class constraint has been staged. Using stage the type class constraint, you can rewrite the definition of power like this. Here, we use code C to stage this type class constraint number A, and after elaboration, this because type class constraint becomes a normal parameter, we can use code to stage the dictionary. So that means after elaboration, no extra type constructor is needed. And also, inside this definition, we will automatically insert splices and quotations to adjust the level of the dictionary to make sure they are well staged. So our next question is, how can we automatically insert the splice and quotations? This is done in a process called constraint resolution. So let's first look at how constraint resolution works for normal type classes. If we define a function inc like this, and after elaboration, it will become expression in the purple box. And what happens here is that when we elaborate the body of the function, the plus notation requires a dictionary for number A, and which we insert through the process of called constraint resolution that basically says under the type context, a constraint C can be resolved by inserting the dictionary E. Here, I'm showing the very basic form of constraint resolution where we just look up the dictionary in the type context. And we can resolve the dictionary for number A in the definition of inc using this type judgment, use this constraint resolution judgment. And with staged type class constraints, the constraint resolution process, just like typing, needs to be level indexed. So a dictionary is introduced at a particular level, and it can only be used at that level. Moreover, we can resolve a constraint for code C at level n by looking up a dictionary for constraint C at level n-1. And the resolution result is simply the quotation of the resolution result for C. And similarly, we can resolve a constraint C at level n by looking up a dictionary at level n-1, and the resolution result is a splice. This is like the specification of the constraint resolution, so you may just observe that these two rules are cyclic. But in principle, in practice, we can break the cycle by always just storing a dictionary for constraint C. So whenever you are given a code C constraint, you can immediately splice it and then store the dictionary at a higher level. So in that case, you will only need the first and the second rule, but not the third one. Okay, as a summary of the talk so far, we have showed that the unsoundness issue in Haskell and proposed the staged type class constraint as an approach to resolve the subtle interaction between type classes and multistage programming. Now we move to the next part of the talk, where we introduce our core calculus and the definition of splice environments. And we start with this question: how to evaluate staged programs? For example, given this expression, suppose it's well-typed and there is no other splices or quotations inside the expression. How do we perform evaluation? Well, the evaluation order should respect the levels. And we start with 0, so E1 is at level 0, and with the quotation, E2 is at level 1, and with the splice, E3 is at level 0. So if we evaluate this expression at level 0, we should evaluate E1 and E3, but not E2. So this expression will evaluate to something like this, where E1 and E3 reduces to value V1 and V3 respectively. In our paper, we present a formalism to evaluate staged programs that is easy to implement and reason about, by elaborating source expressions into core expressions with splice environments, where each splice is replaced by a fresh splice variable s, which is bound to the splice environment of this quotation. Here, the splice variable captures 4 elements. First, the splice expression, and the type of the splice variable, and the level of the expression E3, and the type context. In this case, the type context is empty, but in general, E3 can contain some free variables, which we will use the type context to keep track of. And if E3 has quotations and splices inside it, then it will become nested splice environments. And importantly, the level of this splice variable is also the level of this quotation to which it is bound to. So namely, a splice is bound to the innermost surrounding quotation at the same level. And what are the advantages of using splice environments? First, evaluation can be described straightforwardly. Evaluation initially proceeds as if there is no staging. And when it encounters a quotation, it evaluates its splice environment, which are exactly those splices inside quotations that should be evaluated in the current stage. In this case, E3. And because we don't look inside the quotation, this also allows quotations to be treated in an opaque manner that gives more implementation freedom about the representation. There is one more subtlety here. As we have said, a splice is bound to the innermost surrounding quotation at the same level. But this scheme does not account for the splices with no such surrounding quotations. For example, if we change the quotation around E2 and E3 to parentheses, then in this case, we can still replace the splice as a fresh splice variable, but there is no quotation to which we can bind this splice variable to. So what should we do? It turns out that such splices are exactly those splices of negative levels, and according to the evaluation order decided by levels, they should be evaluated at compile time. So we will lift those splice environments to top-level splice definitions and put them before the rest of the program. And this also gives meaning to compile time evaluation in our formalism. Our paper presents a complete directed elaboration from the source calculus to the co-calculus and show how the splice environments are generated. We are going to skip the details, but interested audience, please refer to our paper for more details. And in the paper, we also prove that our core calculus enjoys type soundness by proving progress and preservation. And we prove the type-directed elaboration preserves types, which also establish the type soundness of our source calculus. And another meta theory I would like to briefly mention is in our paper, we prove that splices and quotations are dual to each other. That means cancel out a pair of splice and quotations does not change the semantics of the program. And this is proved by establishing semantics for the core calculus and the notion of contextual equivalence for the core calculus. And we prove that axiomatically equivalent source elaborates to axiomatically equivalent code, which are contextually equivalent. Okay, you can find more details about the work in the paper with the full typing rules, the meta theory development, the comparison with the current GHC implementation and our source code, and the challenges of integrating our work into GHC. So in summary, we have introduced our source calculus and our core calculus, and this work provides a solid theoretical foundation for integrating type classes into multi-stage programming. So before I take any questions, I also want to mention that I'm on the academic job market this year. So if you are watching this talk, very likely I have already applied to your university. So if you are interested in hiring me, please feel free to reach out and talk to me. And with that, I'm happy to take questions.
Okay, so I have a question or two from online. So the first question is, resolving type classes and optimizing them away feels a lot like staged programming itself. Is there some formal analogy?
Staging type classes and optimizing them feels like what?
Resolving type classes and optimizing them away already feels like staged programming. Can you make an analogy between normal type class resolution and multi-stage programming that you're doing here?
So I think essentially a multi-stage programming has the concept of separate stages. So you essentially have a process of code generation. So in that sense, a dictionary parsing elaboration is very much like a code generation process where you insert the dictionaries in the program. Although I think they serve very different purpose because dictionary type classes are meant to solve the ad hoc polymorphism, and while multi-stage programming are meant to accelerate the performance of the programs. So I think there are some analogies in terms of code generation, but I think in principle they are very different technologies.
Okay, I have another question from online from Jesper. Does your calculus combine nicely with dependent Haskell? Or are there any problems you foresee with dependent types?
A very great question. The honest answer is we don't know because like further studies will be needed to show like how our calculus can integrate nicely into the existing features of GHC, because as you know, GHC is a giant monster with lots of features. So currently our work is still so the calculus in this paper focuses on the very basic elements of this problem. So we basically just support multi-stage programming and the type classes. But yes, I think there is a line of future work to show that this work, how this work can be integrated with other features.
I think we're running a little short on time, so we'll stop here. But thank you again so much.
Thank you for your attention.